Welcome to Positive Physics. Today we're looking at ultraviolet, X-ray and gamma rays, those sections of the electromagnetic spectrum. Now the wavelength of ultraviolet is about 10 to the minus 8 meters, so we're getting quite small here. It's just shorter wavelength than the violet section of the visible light. Now we need to be aware that there is increased danger with our shorter wavelength electromagnetic waves. So if you think about the electromagnetic spectrum, we move from radio through to gamma rays, and we also then have radio having long wavelengths and gamma waves having a very short wavelength. The other thing that actually changes between that is the energy that's transmitted by those electromagnetic waves. So radio waves have much lower energy compared with gamma, and then with that increased energy there is increased danger. And increased risk due to the exposure to these electromagnetic waves. So let's have a look at ultraviolet first, and then we'll look at X-rays and gamma. And if we go back to this chart, a rough chart here of the wavelength of the electromagnetic wave that's emitted and the intensity, do you remember seeing that with infrared and blackbody radiation? If we increase the temperature, so T1 is lower than T2 is lower than T3, what you can see is that the peak wavelength decreases and the intensity increases. So here, in order to get our very short ultraviolet wavelengths, our temperature has increased. So our ultraviolet is produced by hot objects or high temperature objects, for example our sun, where the temperature is greater than 4,000 degrees centigrade. You can also get ultraviolet produced in a fluorescent tube, and it is used then to produce light. So what we have is in our tube we have two terminals here and a specific gas or mix of gases within the tube and a phosphorescent coating on the outside. And when you put a voltage across the two ends of the tube, the electrons within that gas are excited to higher energy levels in the gas atoms. So if we look here at our diagram, we have an electron which is sat in an energy level near to the nucleus. When that voltage is put across the ends of the tube, this electron is excited, it absorbs that energy and it goes up to a higher energy level, and it then sits at this higher energy level, but it doesn't stay there forever. What it does is it falls back down to where it came from, and in that process of falling back down it emits an electromagnetic wave with a wavelength associated with how much energy it holds. And what we find in the gases like mercury and neon and argon, if we have a mix of those, that the energy that is emitted corresponds to an ultraviolet electromagnetic wave. Now what actually happens in the fluorescent tube is that that phosphor coating that I said that was on the outside of the tubes absorbs that ultraviolet light, and then it re-emits it as visible light. And so that is how your fluorescent tubes work. Now, ultraviolet is useful. Okay, when we go out in the sun, our body can make vitamin D, all right, which is very useful to us, helps us absorb calcium, and we also get a suntan. We're going to come on to why that's not so good as well. We can detect fraudulent banknotes. Okay, we have a part in them now that is formed which actually tells us when something is a true banknote or not. And we can use it as security ink, so people can put their postcode on the back of expensive items in their house and use a UV light that makes the ink glow so that it can be seen, but it's invisible, the ink, to the naked eye. So it's useful, but it can be dangerous. So there's an increased risk of cataracts, and that's where you get the clouding of the lens and the cornea, and which can cause, ultimately lead to people not being able to see. And your skin ages, you wrinkle, and there's an increased risk of skin cancer. That is because ultraviolet is a type of ionizing radiation, and we're going to look at that with gamma and X-rays as well. They are all types of ionizing radiation, and what that means is it's got enough energy to remove an electron from the cells. So it can kill a cell, or it can cause gene mutations, so it can cause cancers. Now, the thing to be noting here is that ultraviolet only can be linked to skin cancer, because it's not got enough energy to be able to penetrate further into the body tissues than just the skin. So any ionizing and damage that it does is on the skin. And hopefully you all know that to be safe in the sun, we should be wearing UV blocking protection. So sunblocks or sun creams, which contain chemicals within them and particles within them, which will absorb the UV of different types. There's various different types of UV, and it absorbs the ones that are most damaging to our skin and bring this increased risk of skin cancer. So that's ultraviolet. X-rays and gamma rays are our final two in the electromagnetic spectrum, and their wavelength, X-rays is about 10 to the minus 10 meters, gammas anything down to about 10 to the minus 15 meters. There's actually a blurry bit in the middle where there is some overlapping of X-rays and gamma rays. And the reason that they've got different names but can have similar wavelengths is because they are produced in different ways, and we'll come on to that. But the thing to note, X-rays and gammas, they are dangerous. They are high energy, they are the most ionizing electromagnetic radiation, and so they are the types of electromagnetic radiation that we really need to be careful of. So how are X-rays produced? Well, X-rays are produced by the collision of a fast-moving electron with tungsten metal, for example. It doesn't have to be tungsten, but it often is in X-ray machines. So you get this fast-moving electron whizzing along. So what we've done is we've put it in a voltage, and we've made it go very, very fast. And it's moving along, and when it hits the metal, all of the kinetic energy that it had is converted into an X-ray. You don't need to worry about how that happens. That's a bit for A-level. But if you want to go and look it up, do, because it's really interesting. So this fast-moving electron hits the metal and it's converted into an X-ray. And that X-ray is then used to take an image of our body. And we've got various uses of X-rays to see the bone structure, for a CT scan, so that's a 3D picture, and also radiotherapy for the treatment of cancer. These are the shorter wavelength X-rays in general, the slight higher energy than the ones we might use to see your bone structure. And what they do is that they can kill targeted cancer cells. But we have to be careful to only target the cancer cells. Now, in a question, it often asks you to give a use of X-rays. You cannot just write X-rays. You need to be more specific than that. So you would need to say to see bone structure, or they could be used, as long as the use wasn't medical, you could say that it was used to identify sharp objects or explosive devices in suitcases, in airports. Now, the difference between X-rays and CT scan is firstly the energy of the X-rays that are used. So you have exposure to a higher dose of X-rays with a CT scan. But what a CT scan does is the X-ray camera and emitter move around the body and take a cross-section through. And it moves as though it's, so to take lots of different cross-sections, and eventually they can put it together to give a 3D picture. So it's often used for scanning the brain to find out whether there's been damage in an injury, for example. Gamma then, well, gamma you should have come across already in your study of atomic structure, because it is radioactive decay from the nucleus of an unstable isotope that produces gamma rays, or the gamma type of electromagnetic radiation. The uses then are also in radiotherapy to kill targeted cancer cells. and also as medical tracers. Now you might be thinking, why would you put gamma inside your body if you didn't have to? Because it kills cells, which is why we use it for radiotherapy. But what medical tracers do is they put a sample of the gamma emitter into the body in a form by which it will be absorbed by certain organs or taken to certain places around the body. So they can then see how organs are functioning and whether one is or isn't functioning properly. And they can detect the gamma outside the body using a gamma camera, because gamma can penetrate right through you. The key thing here, though, is that we use a gamma emitter with a short half-life, because we firstly don't want that person to stay radioactive for very long. They will obviously be emitting gamma radiation while they have the gamma source within them. And secondly, we want to minimize the exposure to gamma radiation and therefore the potential risk of damage to cells. So there is a trade-off between being able to find out what's going on with a medical tracer and actually maybe causing damage in the process. So we've done the uses of X-rays and we've done the uses of gamma. Now, X-rays and gammas are very dangerous. They are highly ionizing, they kill cells and they cause gene mutations like cancer. So we monitor the dose, and you'll have come across sieverts again in atomic structure. It's a unit for the measurement of radiation dose. It's not one you need to remember, but it might be referred to in a question, so it's useful to have heard the name before. And there is a maximum dose of X-rays, for example, that you will be allowed to have in a hospital, and a hospital will monitor the dosage that you have. So if you are having a CT scan, they would try and minimize any further X-rays in the course of a year, to reduce or keep low your dose in sieverts. And obviously that will depend on what they're trying to treat with you and how urgent the need is for monitoring. So there we have it, UV, X-rays and gamma rays.